Alright, it's like the product rule for integration, and that's because the integration by parts method comes from undoing the product rule for differentiation. So let me go about this derivation. So for example, what happens when you take the derivative of a product? Well, let's recall that formula. So so whenever we have a product U times V, okay, I don't know why it's showing there. Okay, perfect. All right. So whenever we have a product of two functions U times V, we want to take the derivative with respect X, right? That implies that we may need to do some chain rule because both U and V are functions of X. Alright, so well, the formula to find the derivative of a product is U prime V plus V prime U. Alright. Now, what if we wanted to undo this process? Well, so let's go ahead and do the differential. Right, so I'm going to multiply both sides by the x and get duv equals u prime v dx plus v prime u dx. All right. So we undo the derivative by doing the inverse operation to the derivative, which in this case is the integral. All right. So this derivative gets canceled with this integral because these are both inverse operators. Just the same way that dividing is the inverse of multiplying, adding is the inverse of subtracting, e to the ln cancel each other, or ln of v cancel each other. Well, in the same way, the integral cancels the derivative, so that's going to leave us with the following. So that's uv equals, okay, so that's the integral of u prime v dx plus the integral of v prime u dx. Well, and in this case, if we solve for this, let me actually write this in the reverse order, because ultimately what we want to get is the integral of some function u. We can subtract this term on both sides, giving us u times v minus the integral of v du, which is basically our formula that we have here in the definition box. So again, the integration by parts formula really comes from undoing from the product rule. All right. And yes, well, what's usually the tricky part when it comes to integration by parts? So we need to set up into two parts, that's what we call it, by parts, in which one part of the integral will be the u part, which is the one to be differentiated, while the other part of the integration by parts is the part that we integrate to put everything together. Well, so just so you don't go and try and error, what happens if we take the wrong choice of the u, and if instead we chose, well, if we choose the wrong u, we can end up in an infinite loop and just making a problem more complicated than it originally was, and actually won't have any solution. So for this, we use this acronym that you may have seen before if you have seen integration by parts before. This acronym called LIATE. So, what is this LIATE acronym useful for? Well, the L stands for logarithmic functions. The I stands for inverse trigonometric functions, such as inverse sine, arcsine, etc. algebraic functions, and by algebraic functions we mean polynomials, radicals, etc. And the T stands for trigonometric functions, and the E stands for exponential functions, and not only exponential functions of base E, but also exponential functions of bases other than E. That's fine. Of course, they work the same, just slightly, well, they work slightly different. Well, what is this LIATE for? Well, this LIATE is to determine what the U is going to be. So what we're going to do is we're going to look at an integral. Okay, whichever function comes first, that's the one that is going to take the place of U in this case. So, of course, let's have a look at a few examples to see this in action. So let's use integration by parts to evaluate the integral right here. So number one, let me rewrite the acronym LIATE again. Okay, number one, let's start with the L. Do we have a logarithmic function for the first integral, x e to the 3x? No. Okay, the next one, I. Do we have any inverse trigonometric functions? No. Do we have letter A, algebraic function? Do we have an algebraic function? Which one is it in this case? X. X. Okay, so that's the U. That wins to be the U. All right, that means the remaining part of the integral, the dv part, will be e to the 3x dx. All right. Okay, so what do we do with the u? Differentiate it. What do we do with the dv? Integrate it. So du will be the derivative of x, which is simply dx. And then for the dv part, the integral of e to the 3x, well, recall that the integral of an exponential is itself times 1/3 in this case, right? We divide. If for the derivative we multiply by the derivative of 3x, well, for the integral we should do the opposite, which is to divide. All right, and now we have all the elements that we need to perform this integration by parts, and it would be great to actually rewrite the formula. So the integral of u dv equals u times v minus the integral of v du. So let's see. Okay, the integral, in this case, our u times v, well, which in this case our u is the x, our v is the exponential function, so that's x times 1/3 e to the 3x minus the integral of v, which is also 1/3 e to the 3x du, which is dx. Okay, so for the first term we can just rewrite it having that factor of 1/3 in the front, minus, I'm going to take out this 1/3, integral of e to the 3x dx, and while this integral of e to the 3x, we already did it, that's going to involve another factor of 1/3, so that's 1/3 x e to the 3x minus 1/3 times another 1/3, the one that comes from integrating the e to the 3x. Again, notice for an integral that is this simple, you don't have to show me the u du part, the u substitution, okay? So for integrals that are this simple, it's fine that you show me the fluency that you have by just dividing by that numerical factor that multiplies the x. But of course, for something a little bit more elaborate like x cubed or even another more composite function, it's better to show that part, all right? So plus c, and then let's just 1/3 x e to the 3x minus 1/9 e to the 3x plus c. And that's final answer. That's our first exercise on integration by parts. Questions about it? Okay, let's have a look at the second example. We have the integral of ln x over x squared with respect x. All right, so number one, let's go with the Liate here. Again, of course, that should be very, very useful. But first, I would rewrite the integral in a way that we don't have denominators. So what I'm going to do here is x to the negative 2 ln x dx. All right, so let's start with the Liate acronym again. L, which stands for ln. Do we have for logarithmic function? Do we have any logarithmic functions? Well, yes, that actually has to be our u. Of course, I mean, think about this. We don't have a formula to directly integrate the natural log function in the same way that we have one to differentiate it. In fact, integrating ln of x itself requires integration by parts. So in this case, so u equals ln x du equals 1 over x dx. Okay, so dv will be the remaining part, x to the negative 2 with respect x. And well, to integrate this one, dv, that's going to add 1 to the exponent. So negative 2 plus 1, that's x to the negative 1 divided by negative 1. And let's reduce this to negative 1 over x to have a more proper notation for this. All right. So now that we have all the parts that we need for the integration by parts, let's do the integration by parts. So the integral, the integral of x to the negative 2 times ln of x with respect x will be, on the one hand, u times v, which is ln of x, times, I would put parentheses around this one, because a very common mistake is to divide out these two. What's wrong with dividing out these two, by the way? And get simply ln, like a muted function. So no, that doesn't really make sense. And the reason why we cannot do this cancellation, it's because the x inside of the absolute of the or the argument of the natural log, well, it's protected by those parentheses or absolute value, depending on the case. So we can't cancel that one. Minus the integral of v, which is again negative 1 over x du, which is 1 over x dx. Alright, here I think I should use a little bit of notation just so you can see what part is which. So this is the u, this is the v, minus the integral of v du. Alright, just so you can identify all the parts, because a lot of signs are going on over here and a lot of terms, a lot of parentheses. So okay, so I'm going to multiply this 1 over x in front of the ln x, negative 1 over x ln x. Okay, here negative times a negative becomes a positive. Integral of 1 over x times itself, it's another 1 over x squared dx, which is basically the same integral we just evaluated here, but I'm going to write all the steps. And well, the integral of x to the negative 2 we already did. This is negative 1 over x ln x minus x to the negative 1 over negative 1. Be careful with all these negatives going on here. And don't forget the plus c. So that's a negative 1 over x ln x plus 1 over x plus c. Final answer. Oh, wait a minute. No, this should be a plus. That's fine. And that's what you were going to say, right? Yeah, I read your mind, and that's how I knew, right? All right. right, let's have a look at another example. Let us see what do we have. Arcsine. Let's recall our Liati again. It's already up there. Number 1, logarithmic. Do we have any? No. What's the next group? I, for inverse trigonometric function. Do we have? Yes, that's the one that we have. All right, so in this case, the arcsine will be the u part. And well, let's take the derivative of arcsine, which is 1 over the square root of 1 minus x squared dx. And on the other hand, the dv part will be the remaining part of the integrand, dv, which is dx. Integrate these two, v equals to x. All right. So let's use the integration by parts formula. So, okay, let me write it over here. So, this is equal to u times v, which in this case is arcsine x times x minus the integral of v, which is x, times du, which is 1 over the square root of 1 minus x squared dx. Again, let me do some notation just so you can see which one is which. Alright. So this is our u, this is our v, and this is our v du. Before continuing with this integral, let's rewrite it in a more friendly way. Number 1, I'm going to write this x in front of the arcsine minus the it's not enough space here. X arcsine x minus the integral of x square root of 1 minus x squared dx. Alright, so the first term, x arcsine x, we're done. Let's look at the remaining integral. Any ideas on how to evaluate that integral? Adrian? Yusuf? Looks like Yusuf is fine because look at the quantity inside of the radical is 1 degree higher than the one that multiplies the dx. And even if it didn't, and if it weren't the 1 degree less, recall that in a situation like that we can use the 3 ingredient substitution, right? There's a plan B for those situations. So let's see, Yusuf. So u equals to 1 minus x squared, du equals to negative 2x dx, and x dx equals to negative 1/2 du. Alright? So let me continue over here. X arcsine x minus the integral of negative 1/2 du over the square root of u. And well, let me take that negative 1/2 outside, but be careful because we have a negative from the integration by parts formula that gets multiplied, turning that into a positive. And well, this radical u in the denominator, 1 over square root of u, is the same as 1 over u to the 1/2, which is u to the negative 1/2. Alright? Let me erase this work, okay? And well, the integral of u to the negative 1/2, add 1 to the exponent, and then divide by that new exponent. So negative 1/2 plus 1. So x arcsine x and plus 1/2 u to the 1/2 over 1/2, which is nice because see how these 1/2 cancel, and that's due to the 1/2 which comes back to radical, and we can also back substitute for what we did for u. So x arc sine x plus the square root of 1 minus x squared plus c. And that's final answer. Just so we can see a connection between this and what we have done before, I believe we did the derivative of this function in 7.5, and now we're integrating this to get the original function. So we can see that both results can be checked by differential and integration depending on the case. All right, let's see.